The most expensive component in your data engineering setup, the GPU, is actively wasting 30 to 50% of its potential energy on Windows simply because the operating system refuses to let it sleep efficiently. While developers debate Linux versus Windows as a matter of hacker culture or user interface preference, the hardware reality is starkly different. The truth is that you are burning money and generating excess heat without any gain in throughput just by having your machine running an incompatible OS for serious AI workloads. This isn't about which desktop looks cooler or which keyboard shortcuts feel more natural. This is a direct engineering question of whether your expensive hardware can communicate at full speed with the rest of your system, or if it has to wait behind layers of abstraction that Windows fundamentally blocks. For professional data engineers running local large language model training or heavy ETL pipelines, making this switch isn't an aesthetic choice. It is a requirement for maximizing return on investment and thermal efficiency. Let's look at where the power waste actually happens. If you are using an NVIDIA RTX 3050 Ti laptop today, switching from proprietary drivers to open-source modules can have idle power consumption, dropping draw from roughly 14 watts down to 7 watts. This is a massive discrepancy for a component that should be dormant when not in use. The issue tracked in the NVIDIA kernel repositories highlights that proprietary drivers on Linux often prevent GPUs from entering low-power states like video memory self-refresh, causing significant background activity even when no processes are running. Conversely, Windows defaults often handle idle power gating better than early-stage open-source configurations for certain displays, but this advantage vanishes the moment you start actual heavy lifting. On high refresh rate monitors, Linux with standard proprietary drivers can consume nearly double the wattage of their Windows counterparts due to inefficient power gating in the display subsystem alone. This represents a 17% efficiency penalty on the screen before you even touch your code. For anyone paying for cloud compute or running local training pipelines, this idle drain forces hardware upgrades sooner than necessary because the system is fighting against its own thermal limits rather than optimizing performance. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The real cost of familiarity becomes apparent when we move from idle states to active workloads where bandwidth matters most. Windows relies on a display driver model architecture that introduces kernel-level latency and abstraction layers, which limit direct peripheral component interconnect. Express access required for high-throughput data movement in distributed training. Linux, utilizing the Direct Rendering Manager subsystem with properly tuned drivers, allows near-native bandwidth utilization essential for moving large datasets between Central Processing Unit random access memory and graphics processor video RAM without OS-induced serialization delays. Consider the trade-off you are making right now. Windows offers automated control panels that hide low-level registers required to stabilize specific hardware configurations, while Linux allows direct manipulation of system files to force stability where standard drivers fail. This might sound technical or intimidating if you are used to clicking buttons in a graphical interface, but it is exactly what enables the deterministic performance needed for production-grade data engineering. The perceived difficulty of using command-line tools like PowerTop or editing sysfs parameters is outweighed by the ability to tune frequency caps and voltage limits that GUIs on either operating system simply cannot match for deep optimization. When we talk about containerization, which is the backbone of modern data pipelines, the gap widens even further. Docker and Kubernetes run natively at the kernel layer in Linux environments. On Windows, these tools rely on a lightweight virtual machine or translation layer that adds overhead to input-output operations and network stack latency. This creates a performance ceiling for your data pipelines that does not exist when you run them directly on the metal of a Linux system. The result is often slower training times and higher cloud costs because the operating system itself becomes the bottleneck, preventing your GPU from utilizing its full potential during critical computation phases. There is also a stability paradox to consider regarding hardware longevity. While Windows drivers may seem more stable out of the box for general use, specific issues like AMD RX 5000 series instability are often solved better in Linux via command-line overrides than through auto-tune software that fails to address root causes. By reducing idle wattage from 14 watts down to 7 watts, You extend component lifespan by lowering thermal cycling stress on solder joints and capacitors over years of operation. This is a critical factor for professional engineers who cannot afford hardware failure in the middle of a multi-day training run or an automated data ingestion job. If your pipeline runs on Windows, you are likely burning 15 to 20% more electricity without any gain in throughput because the OS is fighting against power management features that Linux respects and manages efficiently. For cloud users moving this logic to platforms like AWS or Azure, understanding that Linux containers utilize hardware resources more efficiently means you can often achieve higher throughput per dollar or reduce instance sizing requirements for identical workloads compared to Windows-based instances. The decision to switch isn't about adopting a new culture. It is about removing the physical barriers your current operating system places between you and full machine performance. The verdict should be clear. If your goal is serious data engineering hardware efficiency, use Windows for general desktop tasks where graphical conveniences matter, but make Linux, specifically Ubuntu or Fedora, your primary environment for any AI training or heavy data processing to maximize return on investment. You are not adopting a new operating system because it looks cooler. You are switching because the current one acts as a bottleneck that physically prevents your expensive GPU from communicating at full speed with your CPU and memory subsystems, wasting resources you cannot afford to lose in professional workflows. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.